In this video, we're going to talk about another reaction. Yeah, we're going to add another one to our Batman tool belt. That's what I keep calling it because we're going to be able to pull all of these reactions out of our tool belt a little bit later on, depending on what we need to do with them. And in this video, we're going to focus on halogen. Just old halogen. That's it. Just the halogen groups. Now, typically, the halogens that we like to use in organic are Cl2 and Br2. These are diatomic. I think you probably learned about diatomic in Gen Chem. If not, I'm sorry. But diatomics, it was the magic 7. Okay, there were 7 of them. They started at atomic number 7, and it made a 7 on the periodic chart. Yeah, that's right. That's why I call them the lucky 7 or magic 7. There's 7 in total. They start at atomic number 7, and it makes a 7 on the chart. Hope your general chemistry instructor told you that. If not, you missed out on a wonderful experience. All right, so let's talk about where the bromine and chlorine is located. That's the halogen group right here. So chlorine and bromine is going to be located in that stick or the stem of the 7. And these are really the only 2 that we talk about. The reason is that fluorine's diatomic as well, but fluorine, the problem here is that it's too reactive. Okay, this is extremely high in electronegativity. So if we put this into an organic reaction that has some double bonds and some negatives that are there with electrons, you can imagine the fit that fluorine's going to take. I mean, imagine you take a kid into Walmart and that kid burst out screaming, crying, slamming on the floor, kicking their feet and their hands and knocking stuff over. You just want to slap it, right? Well, if that's fluorine here, you just want to slap them. That fluorine is too reactive to be taking part in any of these reactions. And for that reason, we leave fluorine off. I mean, I've mentioned that before, and I'm going to mention it again. We leave fluorine out of here whenever we can. We just don't like to work with it. In addition to that, we're also leaving off iodine in the halogens, right? Because we're talking about the halogen reactions. Why aren't we talking about these 2? Because that's diatomic as well. Wouldn't that work? And the answer is, yeah, it does work, but we just don't see that often either. I mean, we can, but the problem is that iodine is just too big and fat. And the reason that I say that is because these 2 atoms are going to have to be next door to each other. And there's no room. There's no room for them. Because of that, iodine becomes very uncomfortable. And it doesn't like to go on these reactions for that reason. I mean, unless carbocation rearrangement can happen and separate these iodines from each other, being next door to each other like this, it's not going to work out for iodine. And that's the problem with the I2 molecule in the alkene reactions. So the only 2 that we're going to focus on, the only 2 really, is Cl2 and Br2 for that reason. Okay, now here's the next thing. Do you like that awkward silence? The question is, you told me that we had to have an electrophile. And now you're telling me that Cl2 or Br2 can be used in a reaction? How is that even possible? I mean, before we had to add acid. And that created an electrophile that could then be reacted with the double bond. But Cl2 and Br2, aren't they loaded down with electrons? I mean, I just don't understand here. How are these even possible as far as electrophiles go? Because you told me we got to have both. The double bond is the nucleophile, and we should have an electrophile. So does that mean that something's got to be here in order to give these a positive charge? And if so, how is that even possible? Because there's 3 sets of electrons around those chlorines, and there's 3 sets of electrons around those bromines. What do I mean by that? Well, Br and Br are connected together. Each one of these have 7 valence, which gives you a total of 14. 2, 4, 6, 8, 10, 12, 14. There's the Lewis dot structure of Br2. And then the Lewis dot structure of Cl2 is also the same. It's right here. These are not unequally shared. They're shared equally all the way around. 6 on one side, 6 on the other. These are non-polar pieces. How on earth can we get positives out of them? Well, maybe. Maybe. We can get electrophiles out of Br2 and Cl2. One of the things that we can look at is something that we call a bond dissociation energies. Typically, these are tables. They're tables in the back of a textbook or online. And it will tell you the amount of energy to break a bond. That's what those are. How much energy do I have to put in to rip those bromines apart? How much energy do I have to put in to rip the chlorines apart? And that's what we call dissociation. And that's what that really stands for. You're disassociating them from each other. And what we're going to find out is that if we look up those bond dissociation energies, I'm not going to bring that into the picture. I'm not going to write down some numbers and show you the tables. All of that not really called for here. But you're going to notice that these are going to be easily broken. It doesn't take a lot of energy, folks, in order to get this done. So that means in a reaction, this cleavage can happen very easily as well. It's not going to take a lot to break them apart. If they do break apart, typically what will happen here is that these two identical twins will look at each other and say, you're not taking everything. You know, you can leave out of this house and you can take everything that mom and dad had bought you, but you're not going to take everything that they bought for us, because they bought it for us, not just for you and not just for me. So you're going to leave some of it behind. So when these bonds do begin to break, what we end up seeing is that one, it's going to get short end of the stick. That also means that one of these will go negative and one of these will go slightly positive. There's where our electrophile comes in. If these bonds were not easily broken, and if these halogens were not electronegative like they are, and electron greedy and fight over the electrons, then this never really would happen. But we're going to end up getting some slightly negative and slightly positive pieces when these bonds begin to break. Well, what does that mean? All right, so let me kind of just jump to it. Let me just give you an example. Here we have CH3, and then CH double bond, and then CH2, and let's add Br2 to this. Okay, no big deal. We look at this Br2, and this is going to be a little bit different, because we've so used to see hydrogen going on first, right? Hydrogen, hydrogen, hydrogen. But here we have two Br2s that need to be split down the middle. Folks, the procedure's the same. Okay, we'll talk about mechanisms, but the procedure is the same. And in the procedure, what we did is that we said, okay, we'll redraw the starting reagent that we used. There we go. We double bond, and then two sites of attachment open up, and hydrogen goes on the first. Well, we don't have a hydrogen here. We have a Br and a Br. Well, good news for us is that they're both the same. So Br goes on first, and then that creates a carbocation. You might want to double check carbocation rearrangement to see if it would happen. And then in this case, it doesn't happen. So what we would do is we would draw the other bromine there. I mean, this is what we've used up to this point, right? So I've just basically used what we've talked about. Now we'll talk about the details, the little intimate details of this reaction. But at this point, this is how you would have answered that. And it looks like bromine would go onto one carbon and bromine would go on the other carbon. And you would be correct. This is the product here. That's correct. That is right. Good for you. Again, you're learning. You're learning. You're learning. Well, if this was chlorine instead of bromine, guess what, folks? There's no difference. Okay, if that was a Cl2 that was there, it would be a Cl1 and Cl on the other. And then here, instead of BRs, the chlorine would go on first. It would free up a spot, and the chlorine would go on the other. There's no difference there either. That is the beauty of the halogen reactions. Now, let's start getting nitty-gritty. Let's really start talking about this reaction and all of the details that come along with it. And the first one here is a solvent. Okay, so here's the issue with bromine and chlorine. Cl2 is a gas. It's a greenish gas, somewhat poisonous, actually, if you're not careful. You don't want to be breathing that stuff in. So keeping this greenish gas in solution is going to be kind of hard. I mean, what are they saying? I've got a tank of chlorine that's there, a tank of chlorine, and then I'm going to be pumping that tank of chlorine into this alkene? No, not really. There's a better way to do it. Bromine is very similar. Bromine is going to be reddish brown in color. Bromine is a liquid/gas at room temperature. It's actually one of those things that if I pour it into a container and leave the lid off, it's going to evaporate right in front of me, and it's going to evaporate in a red fume, and I can actually see it begin to fill up the room if I allow it to happen. So literally, I can take bromine, which is a liquid in a closed container, take the cap off, pour it into a beaker, and right in front of me, it will start to boil a little bit by definition, and it will begin to evaporate, and it will turn into a gas, and it will eventually just go away. Well, this is a problem too, because how do I make sure that this stays in solution? Well, we need a solvent in order for that to happen. That solvent we're going to write here as DCM or MECl2. So DCM stands for dichloromethane, and MECl2 stands for methylene chloride or methylene dichloride. Both of these are the same, folks. There's no difference. One of these, which is this top one, that's the IUPAC name, and this one here, this methylene chloride, is typically how it's actually said. They even leave the di off of it, is going to be a common name for that structure. Dichloromethane or methylene chloride. That is the solvent. So if I take a look at the structure of the solvent, I hope that it's going to be nonpolar, because this was nonpolar. Cl2, there wasn't unequal sharing there, was there? Br2, there wasn't unequal sharing there either, was there? No. These are nonpolar compounds. They're organic in nature, in a way. So here at dichloromethane and methylene chloride, I hope that this is nonpolar. Let's draw it. Well, how do I draw it? Don't Google it. Do you better not Google that? Because you know what that IUPAC name stands for. Dichloromethane. Methane is one carbon. There we go. Dichloro means that there's two chlorines on that carbon. There you go. And then the other two bonds will be hydrogens. There's the structure for methylene chloride or dichloromethane, also known as DCM or MECl2. Folks, this is a nonpolar compound. There is equal sharing. The top pole is equal to the bottom pole. The way that this is oriented, all four of these bonds are identical and same. So one cancels out the pull of the other. Well, that's good news. It's nonpolar, so therefore this is also going to be nonpolar. So this is how one of the intricate details, this is how we explain the halogen reaction. The problem that people have is that here is really designated for a catalyst, but this is not really a catalyst here. All right, this is a solvent. It just helps bromine and chlorine stay in the solution that they're in. That's really the only purpose of it. It helps the reaction go forward. However, it does not get used up. It doesn't contribute to any products, nothing. It's there, it suits a purpose, it's a solvent, and away we go. So if you do see DCM or MECl2 on this arrow, I want you to ignore it. It doesn't mean anything other than they're trying to be prim and proper, and they're trying to tell you what solvent they are using to keep the bromine or chlorine, which is the most important pieces of that reaction, in solution. Now, let's talk about the mechanism. The curvy arrows. How does this actually even happen? This is going to give you some insight about the individual steps that's involved in this reaction. And the reason I'm going to show you this is because it is somewhat different than some of the other ones that you've seen before in the past. All right. So I'm going to keep this as a simple alkene. I'm just going to keep it as 2 carbons. That way we don't question rearrangement. We don't do any of that mess. It's just, there we go. Okay. And then I'm going to react with this Br2. We want to show how this actually happens mechanism-wise. And this is how we do it. This Br2 is going to come into the picture. And London dispersion forces could actually momentarily shift polarity over on this side. Remember, we said these bonds were easily broken. We also said that when the bond breaks, they will not cleave evenly. London dispersion has a role to play in this as well, because London dispersion will shove electrons over on one side more than the other randomly at moments in time, something that we can never get away from. And if that happens, this molecule, this Br2, could actually come in to the area where that double bond is located. All right, so here we've got 3 sets of electrons. Here we also have 3 sets of electrons. There we go. Okay. And London dispersion could momentarily create a partial positive and a partial negative piece that's here. If that happens, this bromine will be momentarily attracted to that double bond, which is negative. And the way that we draw this mechanism is we show that bromine can't really make up its mind. So this carbon reaches out, grabs the bromine. This bromine reaches out and grabs that carbon, and we kind of have a 3-way that's going on here. A love triangle. That's what we've got. Both carbons are seeing the same bromine, and bromine doesn't know which one that he likes better. Oh, or she likes better. Why be sexist about it, right? Don't put the blame on one gender. Put it on both. Or all of them. Okay, so we see this love triangle that gets made. This bond is going to end up breaking. And that's really where this arrow is going to begin, is at the negative area. And it points to the positive piece. Well, the problem is that that bromine can also point down to this carbon as well, and we get this kind of circular mechanism that happens with the halogen reactions. Okay, so we have a name for this, and what we call this is the formation of a cyclic bromonium ion. And if this was chlorine, it would be called a chloronium ion. No big deal, right? That makes sense. So that's step 1. Step 1, this is what happens with the mechanism. Br2 or Cl2 comes in. London dispersion plays a role. The weakening of a bond plays the role. We get these identical twins. one of them attracted to that negative bond due to a temporary positive charge on it, and that bromine will reach out and grab both of those carbons and says, okay, I got to make up my mind. What do? I'm getting ready to leave the house. Well, at the same time, it can't have both. It can't have the bond to the bromine up above, and it can't hold on to both of those carbons too at the same time. So there's a piece of this very first step that we're leaving out, and that is the separation of the identical twins. At some point in time, they're going to go on about their own way and make their own life for each other. So that bromine's going to say, hey, you know what? Take them. Whatever. You take them. You go. Good luck to you. Now leave me alone. I'm going to go off on my own, and I'm going to start my own life, and there's nothing that you can say or do about it. And that's what happens here. Okay, well, that's okay, because now what we end up with is the true cyclic bromonium or chloronium ion that begins to form. This is the initial stages of it. So when we do this, that double bond is now broken. I'm going to draw a single one there. And that bromine, I told you, reaches out and it grabs both of those carbons. The problem, though, is that it's also positively charged at this point in time. So that is the formal cyclic ion that we are referring to. Well, notice what happened up here. This bromine, pop, left, and this goes off on its merry little way. It took those electrons and it went bye-bye, and away it went. So we also have that still left over in the reaction. I mean, if I'm putting this into a beaker or to a flask, that's still in there. It's still swimming around. Okay? So we have another part of the mechanism here, because I know two bromines go on to this molecule. I'm just showing one right now. Where's the other one coming in? Well, if you look at this, bromine gets itself into a predicament. This is what they always do. They bite off more than they can chew. And bromine says, uh-oh, I messed up. I'm a positive charge now, and that identical twin already left me. I'm in a bind, and I can't call anybody for help, can I? I mean, I'm just going to have to make do? The answer's no. That twin's going to be there when you need him to be there, or her to be there. So that bromine calls up the other one and says, hey, listen, I'm sorry the way I treated you. You know, I didn't mean to kick you off like that. But I have found myself in a situation and I need some bond money. I mean, I've been arrested. I've been put in jail. I need you to come and bail me out, please. And that bromine or that chlorine is going to say, okay, what do you need? How much? Because that's what brothers and sisters do if you're an identical twin, right? Okay, so if this begins to happen, that bromine is going to get in the car and it's going to drive out and it's going to save its brother or sister. So this bromine right now is negative, and this bromine is positive, and that bromine says, you know what, this ain't working for me, and I've called my twin, and they're coming to bail me out, and it gets an attitude. And it says, I'm electronegative. I want these electrons. So it takes these electrons and sucks them up. And it looked out for itself. Well, when it did that, it only did that when it knew the twin got closer, right at the police station maybe, right? That's when it starts acting all big and bad, like, oh, look at me. Well, this bromine is negative, and it's going to come in, and it's going to attack this carbon that was involved in that love triangle. And there's the next step of the reaction. So this cyclic intermediate is unstable. As you can imagine, this is an unstable step. And the other bromine that was kicked to the curb in step 1, or chlorine, will come in and it will attack one of those carbons. And at that point in time is when that bromine uses its electronegativity to suck those electrons up and engulf them, so that way everything can be neutral at this point. And what we end up with now is a CH2, single bond CH2. This bromine cleaved that bond, boing, over here to the end, that's where that bromine ended up. And then this carbon to the left, that is what got the other second bromine that came into the picture. Folks, that's the mechanism, and it's a little bit different than what we've been seeing in the H halogen mechanisms, the H water mechanisms, the H alcohol mechanisms, right? All of those had a general trend that was happening with them. But the addition of a halogen is slightly different. So formation of a cyclic bromonium or chloronium ion, that cyclic structure is unstable, and that will allow a reaction to happen again. And what we say here is that it creates a vicinal bromide or a vicinal chloride. What the term vicinal means, that's not vinyl, okay? What the term vicinal means is that the halogens, in this case bromo or chloro, are side by side. That's what that means. They are exact next door neighbors of each other, side by side. That also means no rearrangement. Well, how does that be? How's that even possible? That could be your question. And if so, that's great. That's a good question to ask. The reason is that all of this is really, in a way, concerted. It all really happens at one time. So this bromine, in the very first step, grabs onto those carbons and latches onto those two specific carbons and says, I've got to make up my mind on what I want to do. I've got to make up my mind on what I want to do. And then in the meantime, the other bromine or chlorine comes into the picture and grabs the other one that's involved in the love triangle. There is no point of which a carbocation is fully formed and can move. So rearrangement does not happen in the halogen additions for that reason. It's due to the mechanism. That's good news for you, because if you forget to look for rearrangement, well, you can at least get the bromines and the chlorine additions the right way, because those do not rearrange. As long as it's a Br2 or Cl2 with DCM or methylene chloride, it will not rearrange on the alkene. That's just the way it is. And those products are always called vicinals, and those vicinals represent neighbors side by side. Okay, so that's where this video is going to stop. Next video, we'll pick up from here, and we'll keep on a-truckin'.